Okay, let's dive into something today. It might seem pretty abstract, maybe stuck in a college textbook, but it actually connects to something really fundamental like, well, food and water.
Absolutely. We're talking calculus, specifically integration.
Right. Integration, and how it surprisingly plays a huge role in keeping crops, properly watered.
Yeah, the sources we looked at really break down how integration helps us understand something called evapotranspiration.
Evapotranspiration.
Okay. And that tells us a lot about whether a plant is actually getting enough water.
You sit through those calculus classes, right?
Yeah.
Try to figure out what an integral even is, and you're thinking, okay, when am I ever going to use this?
Uh-huh.
Well, it turns out people in agriculture, scientists, hydrologists, they're using it like every day.
Constantly
Right.
for really critical decisions.
So our mission for this deep dive is
Good.
basically to unpack that. How does this math tool, summing up tiny changes, tell you if, say, a whole field of corn is thirsty?
Well, it really starts with understanding that term I mentioned, evapotranspiration, or sometimes just called ET.
Okay, DT, got it.
Think of it as the total water leaving the land and going back into the atmosphere. It's two things combined. Evaporation, water drying up from the soil or surfaces.
They're like puddles drying up.
Exactly. And transpiration, that's the water vapor plants release from their leaves, part of their breathing process, essentially.
So it's like the whole system, the land and the plants kind of sweating water out.
That's a great way to put it. Now, the key thing the sources really emphasize is that this water loss, this ET rate, it isn't steady. It changes a lot.
Okay, how so?
Throughout the day, for instance, it's generally higher when it's sunny and warm, maybe windy, lower when it's cool or cloudy.
Right, makes sense.
Plus, different plants transpire differently, and how wet the soil is affects evaporation, too. It's
Well, it's gets you.
complex.
So a plant isn't just losing water at like one constant speed all day. It's speeding up, slowing down.
Precisely. It's dynamic. And if you're, say, a farmer deciding when and how much to irrigate, you don't just need today's rate.
You need the total amount lost.
Exactly. You need the total volume of water lost over a meaningful time, maybe since the last rain or the last time you irrigated. That total tells you how much needs to go back in.
Okay, I think I see where this is heading. If the rate keeps changing, you can't just like measure it once at noon and multiply by 24 hours.
Right. That would be totally inaccurate most of the time.
It'd be like checking your car's speed for 1 second on the highway and assuming you drove that speed the whole trip.
Perfect analogy. That simple multiplication only works if the rate is constant. But ET is not constant. It varies.
Low in the morning, maybe peaks mid-afternoon, drops off evening.
So you need a tool that can accurately add up all those changing rates over the whole period.
And that's integration. That's what it does.
Yes. Fundamentally, integration is about accumulation. It's summing up continuous change. If you can describe that changing rate of ET over time, maybe with a mathematical function based on sensor data or weather models,
Okay.
integration calculates the total amount accumulated under that rate curve over your chosen time interval. And that amount, that area under the curve, represents the total volume of water lost.
Wow. So instead of just guessing or using some rough average that might be way off, integration gives you a precise number for the total water deficit.
That's right.
It turns the constantly changing speed of water loss into the total distance,
Yeah.
the actual volume of water gone over that time.
Exactly. And having that accurate total ET figure is incredibly valuable. It allows for really efficient irrigation, precision agriculture, they call it.
Because you know exactly what's missing.
You know what was lost, so you know what to replace. You're not wasting water by over-irrigating, and you're not stressing the plants by underwatering. It optimizes everything.
It really changes the game for managing water, doesn't it? From rough estimates to, well, precise calculation, all powered by calculus.
It really does. It shows these math tools aren't just theory. They are vital for tackling these complex, variable, real-world problems, like keeping our food supply healthy.
Okay, so wrapping this up then, the key insight from this deep dive, really driven home by the source material, is that integration is this powerful way to quantify total water loss in crops, the evapotranspiration, even when the rate is all over the place.
It lets us manage crop hydration much more precisely.
Yeah, it shows integration isn't just, an abstract concept. It's a practical tool helping solve manageable problems, like making sure plants have the water they need.
Absolutely. It's about understanding and managing dynamic, natural processes better.
Which leaves you, the listener, with something to think about. If integration can help us get such a clear picture of something as complex as the water needs of an entire field, What other complex systems out there, maybe in nature, maybe in industry, with all their own changing rates and dynamics, could we understand and manage better using these kinds of mathematical tools, things you might even be learning about right now?